given the rapidity with things are changing on the planet today, it's really nice to have the context and the history and to understand what it is that goes into the environment that we have today, what it is that supports the planet and life as we know it, and to think about the fragility of some of these relations and also just the incidental nature, and really understand it as we proceed and change things. So, so both of these were sort of the opportunity. But during this talk, I'm primarily going to focus on the particular story that I'm telling that is related to my research, having to do with how, as unlikely as it might seem, dark matter and the dinosaurs might connect. So I'll tell you a little bit about that story and a little bit about the larger story in which it's embedded tonight. So dark matter. You know, it's funny how many people feel perfectly happy to tell me they have no idea what dark matter is. And it's kind of amusing because dark matter is actually one of the simpler concepts that I work on, in the sense that it really is just matter. And what is matter? Matter is defined by how it interacts with gravity. So matter is stuff that interacts with gravity like matter. And in particular, it does things like clump together. So it clumps together into galaxies and galaxy clusters, into objects that we can hold or live on or stuff. And that distinguishes it from energy, like dark energy, that's just spread throughout the universe uniformly. I'll tell you a little bit more about that in a second. But for dark matter, what distinguishes it from what I'm going to call ordinary matter is that as far as we know, as far as we've detected so far, it doesn't interact with light. So it's only interacting with us as far as we know, via gravity. There can be other interactions, too small to have seen so far, but what we do know is that that dark matter has a gravitational influence, and that's why we know of its existence. So that means that if dark matter is made of elementary particles, billions of them can be passing through you every second, and they probably are. But you don't know about it, and that's because it's not interacting with you. Gravitational force of an individual dark matter particle is tiny, or even billions of dark matter particles is tiny. It's only when you have the huge amount of dark matter that exists in the universe that it has enough gravitational influence that we can detect its effects. So although we don't see them, it does nonetheless give shape to the universe in ways that we'll discuss. So if we look at the energy budget of the universe, we find that ordinary matter, which is labeled here as atoms, is only 5%. So the stuff that you and me and this lecture is made of is only 5% of the universe. Dark matter, there's about 5 times the amount of energy in dark matter as there is in ordinary matter. And it's funny, a lot of people get upset by that. Despite the Copernican revolution, people really want to think that everything about them is central to the universe. It turns out it's not the case. In fact, the more incredible thing to me is that ordinary matter is as much of the universe as it is. That it's 1/6 of the matter of the universe. I actually find that amazing because there's no reason for it to be. I mean, after all, the ratios could have been 1 trillion to 1. I mean, I like eating pie, and any of those slices of pie, I would realize I ate some pie. But really, it could have been that one was such a small sliver we wouldn't even know it existed, and you'd be really angry because you're really just getting a crumb. But really, all of those slices are comparable, and that's actually an interesting thing about the universe, that ordinary matter, which is the stuff that we're made of, and didn't really have to be a significant fraction of the universe, is. But dark matter, nonetheless, dominates, and there's about 5 times as much of it. But most of you are probably looking and saying, why is she talking about the matter when dark energy is taking up most of that pie? And dark energy is about 70% of matter, no, I should say of the energy in the universe, it's not matter. And dark energy was what I was referring to earlier. It's stuff that doesn't clump. It's stuff that's uniformly distributed throughout the universe. And not only is it uniformly distributed, but it also doesn't dilute. So as the universe expands, and we do live in an expanding universe, ordinary matter dilutes, radiation dilutes. It carries less than a fraction of the energy as the universe expands. But dark energy stays the same. It's just a constant. And again, it's a large fraction of the energy of the universe. Actually, the weird thing about dark energy is the puzzle is not why there's so much of it, but really why there's so little of it. Dark energy is something that's completely consistent to have. There's no reason we can't have this energy. And the question is, why should the amount be comparable to the amount of energy we have in matter? And that is actually a really interesting question that we don't actually know the answer to. So, so a lot of people, look at this and they get very upset. They think, look, all of that's dark, and we don't know what that is. But actually, it's an incredible story that we actually know what this is, that we actually know what these pieces are, that we understand the evolution of the universe well enough to be able to pin down that these are the components. And although we don't know what dark matter is made of, we do know very well that the dark matter exists. And in terms of ordinary matter, we do know a lot about what it's made of. So we know all of this because we actually now have a very accurate theory for the evolution of the